Hey, all you cool cats. So this is the supplementary notes video. Basically going to cover uh, three three problems, but talk about like the ideas behind them and how they relate to everything that we did in lecture two. All right. I will try to speak normally. I know I spoke very quickly during that last lecture, so I'll try to take my time a little bit with this one. All right. So let's just jump right into it. We did integration by parts in the lecture during lecture, but there are some special cases. There are two special cases with integration by parts. One, I like to call it grit method. In the book, they call it repeated use of integration by parts, and it just sounds so boring. But grit method, it's going to require a little bit of grit to get through. And then the tabular method, China's actually just going to cover this during recitation with you guys. So yeah, I just wanted to try to make these videos shorter, so we'll see. And then I'll follow up with the other two cases of trig sub from our lecture. All right, so let's talk about grit method. This is example 5 actually from your textbook, page 419. I think they titled it like, "Oh, going in a circle" or whatever. But yeah, here let's talk about why it's called. We'll talk about why it's called this grit method and so this is a kind of fun example. I mean, I think it's fun. But if we use that acronym I showed you guys during class today, LEPET, right? If you don't remember, LEPET was the thing to helps you choose the U function, right? Not the dv function for integration by parts. Well, I have two functions here. One of them's e to the x and one of the other one's cosine. And I see that exponential functions come before trig. So, intuitively, I'm gonna choose u to be e to the x, while I choose dv to be cosine of x. Okay, this means du is going to be e to the x again, and v is going to be sine of x. And I kind of briefly mentioned this during the lecture, but we noticed that e and t is actually at the end of our thing, and the reason why they're at the end is because when we choose a u, we normally want the u to kind of cancel something out or to kind of go away. But in this case, both the exponential and trig functions, they actually keep reoccurring, right? They just keep on coming back. So let's see what happens on this example, and you'll you'll see why it's called the grit method in a second. All right, so let me use our formula here: ultraviolet minus integral of voodoo. All right, and let's plug everything in. So we get e to the x times v, which is sine x, minus integral of voodoo. So v again is sine of x, and du in this case is e to the x. And you look at this, and you're thinking about that theme that we talked about during our lecture. Did we rewrite this into something that we can integrate? Well, if I look at the integral, I don't know. Doesn't it kind of look like this, except just with a sine of x? And you're just kind of like, well, what did we really do? Like, it's like we did nothing, right? So do we just give up? No. This is why it's called the grit method. Keep on going and see what happens. Okay, like in life, right? Sometimes when it gets a little hard, sometimes you just got to kind of push through and see the light at the end of the tunnel, right? So, trust me, it's sometimes. I mean, it does work out, with this grit method. There are times where it won't, and but yeah, don't worry. Like, we're not going to give you those types of problems with you like after you do a couple of these, you'll be able to spot like a grit method problem. Most of the time, it's just going to be like one of them's like an exponential and the other one's a trig. So that's usually what the grit method is for. So watch if I do this again, right? I used up my u and v, so actually I can kind of use them again, right? I can say u is equal to e to the x again, du is equal to e to the x, dv is sine of x, and then v is negative cosine x, right? So what's going to happen? Well, this first piece we're just going to leave alone. That one just drops down, comes along for the ride, right? E to the x sine of x. But the second piece, we are actually going to have to use integration by parts again with this new set of u's and v's, right? So why don't we do that? So it's going to be minus, I'm going to put a parentheses, and now we're going to have to do the uv minus integral of v du again, integration by parts. So watch, we get e to the x times negative cosine of x. Okay, just watch out. The negatives get a little finicky. Minus the integral of v this time is cosine x. Okay, I just changed the sign in front of the integral to positive. And then du in this case was e to the x again. All right. Why do I need the parentheses? Because we are, once again, doing integration by parts, and this pesky negative needs to run through the whole thing. All right, just basic algebra rules. So watch, I'm going to clean this up a little bit. Let's see what I get. E to the x sine x plus e to the x cos x plus integral of e to the x cos x dx. Whoops, I made a small mistake. That should be a minus sign. Oh my gosh, the negatives even got me, right? Because once again, this negative out here distributes to both of these terms, all right? So this is what we have, all right? And we're looking at this line and we're like, well, that didn't really help. Way to go, John, right? But look at the piece that we have here. This piece should look familiar, right? Does it look familiar? It should. That is our original problem. And you're like, oh snap, he's not going to do it, is he? Yes, I am. Look, it's algebra. I can add this piece onto the other side, right? It's just like combining like terms. Essentially what I'm going to do is add integral e to the x cos x dx over to the other side. So this becomes plus integral e to the x cos x dx. And look at what happens. We get two of them now on the left side. And then on the right side, we're left with e to the x sine x plus e to the x cosine x. And I'm just going to add that plus c just because, we integrated something indefinite, right? So that always means we get a plus c that comes out no matter what. And we're just one step away, right? All we have to do is divide everything by 2. Divide by 2. Divide by 2. The c just ends up being another c. And you're left with the final answer. This guy right here. Right? So what happened? We kind of saw that there's an e to the x sine of x that appeared when we used integration by parts, but we kept on going and saw that the original problem, this piece right here, the original problem reappears in our work. And if that happens, or I'm sorry, some form of the original problem, because it's not always going to be like a 1. Sometimes there might be like coefficients that come out. You'll see in your homework. But in the original problem, some form of it, some multiple of it will come out. Therefore, you can add it to the other side and then kind of simplify it that way. All right, so that's pretty much how the grit method works. All right, and that kind of is it for integration by parts. Like I said, China will do tabular method with you guys. Let me move on to the trig sub, which was 7, I believe 3. In class, we talked about the three forms that you guys will come across. All right, so the 3 forms are square root of a squared minus x squared, so that's 1. The second form is square root of x squared plus a squared, or the other way around since, it's addition. And then the third one is square root of x squared minus a squared. All right, and I had said that the first one you use this substitution. For this one, you use tangent. And then for the last one, no, wait, I screwed that up. Sorry. Please use these notes. This one is going to be, oh wait, no, I did have it. Yeah, it is the tangent. In fact, in the book, they actually put the a's here, like the square root of a, right? I'll explain that in a second. And then for this one, you get a tangent. And then for the last one, it's a secant. So I think this does line up with what I said during class. All right, and if we use, as long as we see these forms, the square root of whatever form in our problem, we can use trig sub to kind of rewrite the integral. Right. So we did an example of number 1 already in class. So I'm not really gonna do that again. Just refer to the video. So why don't we look at ones that look like 2 and 3. So let me just pull up an example real quick. All right, so let's look at this example right here. 1 over square root of x squared plus 9 dx, okay? So we notice on this one, our a term is actually 3, right? Because a squared gets you 9. So you got to kind of think in squares a little bit on this one, right? If I look at the form, I see x squared plus a squared, which tells me I'm using the x equals tangent theta substitution, right? So we're doing this one right now, right? We're going to use that, right? I see that form in my problem somewhere, therefore I'm going to make the substitutions and yada yada yada. So I had mirrored that problem, example 1 that we did in class, to like use sub, because that's kind of what we're doing, just with a little bit more trig. So watch, let's mix the substitution and see what we get. We get 1 over square root of, it's not x squared anymore, it's tan squared theta plus 9. and we have to substitute out this dx. Oh my gosh, I forgot about that a, didn't I? Yeah, so when we make the initial substitution, we have to account for that a value, okay? So just take a note of that. So this actually ends up being, and you'll see why we do that in a second. All right, so don't forget about that a. Next, we gotta substitute in for this dx and see what happens, right? So I jump to my original substitution here, and I derive. I get dx is equal to 3 secant squared theta d theta, right? Because the derivative of tangent is secant squared. We make the substitution and see what happens. This becomes integral, right? Because I haven't integrated yet. So the integral of 3 secant squared theta d theta, right? Because that comes from this substitution right here. I substituted 3 secant theta in for dx. And then all of that is over. Well, let's do some factoring here. Square root of 9 tangent squared theta plus 1. Hopefully this should now explain why we needed that red 9 there, right? It's because we needed a form of tan squared theta plus 1 using our trig identities. All right, so watch what happens. We do a little bit more simplification. We get the integral of 3 secant squared theta d theta. I'm just going to leave the top alone. On the bottom, I have 2 square roots, right? I have a square root of 9 and then a square root of tan squared theta plus 1. Well, if we know our trig identities, we know that that's equal to secant squared theta. Haha, right? So we get square root of secant squared theta, which is going to reduce down to regular secant. And then the square root of 9 becomes 3. And look at that. We get things cancel out beautifully, right? And then you're left with integral of secant theta d theta. Now, I know you guys probably don't know this one off the top of your head, but you can prove the integral of secant theta using, just a simple rewrite. You just rewrite it as 1 over cosine theta, and then, just basically take it from there. But basically, you get ln of absolute value of secant theta plus tan theta. Actually, now that I remember, there is like a trick you have to do to do the integral of secant theta. So, but yeah, you end up getting ln of secant theta plus tan theta plus c. And so now we get to the end of the problem, right? We're like, oh yes, we finally integrated, but once again, it's rude, right? This is kind of rude. You're leaving an answer in terms of theta when a problem was given in terms of x, So we have to change our thetas into x's. So we go all the way back to our first definition here, x equals 3 tangent theta, and we have to figure out how to rewrite secant theta and tan theta. All right, so this part's kind of tricky. I remember when I first learned trig sub, I didn't really understand this in the beginning, but it really, really helps if you just draw out a triangle, right? We're dealing with trig, so it makes sense. Just draw a triangle and see what happens. Like, watch. I'm going to draw a right triangle because it's trig. And additionally, I'm actually going to rewrite this as x over 3 equals tan theta. All right? So if this is true, if this definition is true, then I can mark a theta. And since tangent is opposite over adjacent, I can write x over 3. X and 3. Well, using Pythagorean's theorem, I can figure out that third side and use it to define secant theta, tangent theta. Yes, I know, it's crazy, right? Watch what happens. So I'm going to get this third side. It ends up being x squared plus 9 is equal to that third side squared, which means it's going to be the square root of x squared plus 9, right? That's what this third side is equal to. Now, using this definition, right? Using this definition, could you tell me what secant is? Well, secant of theta, that is when you have cosine but flip it, right? So cosine is adjacent over hypotenuse. So this would be hypotenuse over adjacent. And in this case, it's root x squared plus 9 over adjacent, which is 3. So what did we just do? I just defined secant theta in terms of x using trig. Pretty gnarly, right? I know. So let me rewrite this. This becomes ln of absolute value, square root of x squared plus 9 over 3, plus, well, what's tangent theta? Wait, didn't we say that earlier? Tangent theta is x over 3. So we just write x over 3 plus c, whoops, come on, plus c, and there it is. That's our final answer. Is it pretty? No, but it is in terms of x, and that is all we care about. All right? So that's that example. Oh my gosh, 17 minutes. Oh, I'm sorry, guys. We're moving on to this. If you want to stop there, you can. The third example is pretty much the same thing. Just with these problems, okay? There's always a part. There's always a part. In this case, it was here. There's always a part where everything kind of just gets beautiful and just cancels out so deliciously, right? Like the 3's in this case canceled out. The secant canceled out, leaving you with something like integratable. It's always going back to that theme, right? Just remember that. All right, so I'm going to do this third example, but you can stop here and try the homework and stuff, or I guess when it comes out, or rewatch, whatever. Okay, so the third example is, let's see here, one second. The third example is this guy. Integral of dx over x squared, square root of x squared minus 9. Ooh. Seems kind of weird, I know, but we notice the form, right? Or I guess let me start from the beginning. I'm given this integral, and my mind process, my thinking is this. Well, I see an x squared minus 9. I can't really use the product rule on this. Okay, I can't really use u sub on this because x squared is on the inside and it's on the outside. But I do notice this form, x squared minus 9. And that is one of the 3 forms. Where is it? That is the third form right here, right? This means this is the secant one. I have to use the secant definition. So this one, I'm going to go x is equal to secant theta, right? But I cannot forget about my a value. In this case, it's going to be 3, just like the last one. That's kind of unoriginal. All right, whatever. So this one's going to be x3 equals 3 secant theta. Let's derive this thing since we know we're going to need it. So this becomes 3 secant theta tan theta. And let's boogie. Let's see how this works out. All right, so we're going to make some substitutions and see what happens. So I'm going to do this one a little quicker than the last one. dx is equal to 3 secant theta tan theta over x squared, which is 9 secant squared theta, square root of another x squared, so 9 secant squared theta minus 9. And we're just going to do some cleanup here. No integration yet. Just clean up. Simple algebra, right? 3, okay, maybe not so simple, but 3 secant theta tan theta all over 9 secant squared theta. It looks like I'm going to pull out a 9 out of this guy right here, which means a 3 is going to come out of the square root. And then leaving me with secant squared theta minus 1 under a square root. Well, that's tangent squared, isn't it? So this is going to end up being just tangent squared. Where did my d theta go? Oh my gosh, I left it out. Oops, sorry. All right. So we made the substitution, we simplified, and look, things are going to beautifully cancel out. Like I said before, right? Oh, that's so nice. Yes, the 3's cancel out. Yes, the tangents cancel out. Yes, the secants cancel out, right? Leaving me with, it looks like 1/9 on the outside. I could just take that out because it's integral. And then I get 1 over secant theta d theta. But oh my gosh, I don't know what that is, right? Wait a minute. Secant theta, isn't that 1 over cosine? It totally is. So look, this simplifies to 1/9 integral of cosine theta d theta. Mwah! Beautiful. I love it. I love it. Look how nice this looks compared to our original problem. Ew. Right? Right. So here we go. We know the integral of cosine theta, hopefully. It's sine theta plus c, and can't forget about that 1/9. All right? And we're almost there. We just need to rewrite this in terms of x, and we'll be done. So let's see. Let's go back to our original substitution, which is this guy right here. X equals 3 secant theta. I'll write it again right here. X equals 3 secant theta. Now, we don't want to really leave it in terms of like inverse secant. I don't think I said this on the last example because it's not really nice. All right. So we're actually going to do the same thing we did on the last example. We're going to make a triangle and use that to figure out what sine theta is in terms of x. So watch. I'm going to divide both sides by 3, just like before, and I get x over 3 equals secant theta. Well, let me draw that triangle. I'm sorry it's so ugly. Here's theta. And once again, secant is the reciprocal of cosine. So that means it's hypotenuse over adjacent. Hypotenuse over adjacent. So x is the hypotenuse, adjacent is 3, and we got to figure out this third side. I'll call it b, right? So we write 3 squared plus b squared equals x squared. We get x squared minus 9 is equal to b squared. So that means this side is going to be square root of x squared minus 9. And did we need that sign? Oh, we did. We did need that sign because sine of theta is opposite over hypotenuse from theta. So opposite is going to be root x squared minus 9 over, what is it? X, right? Because hypotenuse. Bring the 1 line along. You know what? I'll just put that stuff together at the bottom, make it nice and pretty for y'all. And then plus c, and we are done. Once again, is it a pretty answer? No, but it is in terms of x, which is what we wanted. All right, so that's pretty much it. We covered all 3 cases, along with integration by parts. I'm so sorry this video is even longer than the first one. Ugh. I think it's just how it is. So, if you need to set up a meeting with me for any reason, please do so. And good luck. Good luck with your homework. All right, see you guys next time.